And welcome, we're back, Math 212, and we are looking at, we're going to look at the normal, we're going to look at some box plots, we're going to look at some weighted averages, and let's get started today. A little bit more on statistics. So here are our topics that we will be looking at. In comparing two sets of data, we can use box plots or scatter plots. And we are going to go back to our peanuts problem. We could also look at test scores, it's mentioned here, of two different classes. We could do test scores of the same class, two different teachers, the same teacher, two different classes, and whatnot. All sorts of different combinations that we could do there. It'd be unlimited. When we look at how many peanuts can adults hold versus children, we look at the data, but it doesn't really we can't make a whole lot of sense out of it. They're numbered, so that's nice. We could get a mean, we could get a median, we could find a mode and see how all of those things differed as our measure of central tendency like we did last time, although visuals are just so super nice. So what I did for you is I went to Desmos and I got you a box plot. So let me show you how I went to Desmos and got that box plot. First step, what I did was I just went into my Google search and I typed in Desmos. They have all kinds of different graphing calculators, they'll graph scatter plots, everything. But it's best if you go ahead and type in the type of plot that you want, and then they put it in the format that you would like. So let me show you what that looks like. Okay, so here it is. You can see in my URL, it's desmos.com, but what I typed in my URL was Desmos, D-E-S-M-O-S, and then I typed in box plot, and it came up with this. It had a list in there. Of course, it didn't have my list, but it had a list in there, and all I did was just overwrote their list for mine. So let me key in those values and I'll show you how to do it. And you'll notice it goes ahead and gives me all the quartile values and numbers for these box plots. That's something that you might have your students do, is to find the quartiles. So I'll type in a few of these to begin with. So I just go over here and I pick my whole list. Of course I don't want the brackets in there, and then I just start typing them in: 18, 18, 20, 22, 22, and so forth. I'll finish that up for you. So I got those keyed in for you, and we can see how my quartile numbers have changed. But most importantly, here's my box and whisker plot. Now this is what I usually do, is I will just go to my snipping tool and I'll hit new, and I will grab the picture. Of course, it's going to get a little bit of that in there. All right, there we go. And I'm going to hit Control C for copy. Then I hit Control V, pasted that box plot on here. So now I can look at the box plot. You can see that my children's, their range is from 11 to 25, and the college students 18 to 37. And with this you can see that I have a long set of values here on the right hand side, because I have this one outlier, the 37, that probably should be thrown away, but it still gives me a good idea, and it shows me my middle values here around 25 and the middle value here around, looks like around 19 or so. So that's lovely. It is just letting us look at a visual of our data. Next, we're going to talk about standard deviation and the mean absolute standard deviation. We're not going to do any of these problems, but in the 6th grade, the students will go over this mean absolute deviation, which means I just want to know how each of the different data points vary from the mean, or what that value is. Here on standard deviation, that computation is a bit more complicated, and the students won't see that until high school, so they'll just look at mean absolute deviation in the elementary school years. And this central measure of tendency here, the mean, median, mode, those are all closely related, and standard deviation and mean absolute deviation are not the same, but they're very closely related. It just tells us how spread out the data is, and we could see how spread out the data was by looking at our box plot as well. The normal distribution deserves its own slide. The normal is what a lot of statistics is based on, what statistical testing is based on. It's a big deal. So it might not look like a big deal, but it really is if you're doing statistics. So we're going to collect a whole bunch of data, and if we collect a whole bunch of data on weights or heights or IQ or even how long a tire lasts, how long a light bulb lasts, how much money people have, all of those sorts of things, we're going to get what's called a standard normal, meaning that if we collect enough data, the data will have this beautiful little bell shape, and that's called our standard normal. In the very middle, you will find the mean, and as we go out on either side, we'll find fewer and fewer people, or whatever it is that we're looking at, will have these values here. So while we were looking at that, even though our heights were measured in inches, and this was the actual picture, we could see that if we smooth that out, and we did it, and we didn't just block it off in inches, we did half inches and quarter of an inches, this blockiness here would get smoother and smoother. Now, IQ scores, all kinds of testing scores, all of these are based on a standard normal. So let's look at what this standard normal means. If you are looking at a standard normal and you have the mean would be in the center, 68% of the data will lie within one standard deviation of the mean, and 95% of the data will lie within 2 standard deviations of the mean. So what does that mean for you? Well, I'm going to get my pen and let's look at it with this particular problem here. If I have a mean of 250, so let me just overwrite this with a 250, and my standard deviation is 50, so that means this number would be 300, this would be 350, and this would be 400. This would be 200, 150, and 100. That means 68% of the people score between 200 and 300. 95% of the people will score between 150 and 350. So how many students would I expect to score over 350? I just take these percentages and add them up. That would be 2.35% plus 0.15%, and that would get me about looks like 2.5%. So that's what I would expect to score over 350. How many would I expect to score at least 200? That would be from here up, so I can just add all of those percentages. I'll get those written down. So I've added all of these up, but if you'll notice, what I could have done was just said, from here up is going to be 50% because that's half of it, and then just added the 34. That would have been a quicker way to do this. But it's nice to see that they do add up to that 84%, 50 plus 34. Another one, it doesn't really matter what it is you're looking at, whether if you're looking at IQ scores or if you're looking at how long a tire lasts or a light bulb lasts or whatever. So if the mean is 44,000 and the standard deviation is 2,500 miles, then you just add 2,500. So let me get that out of here. So that would be 46.5 here. Add another 2,500, and I'll mark all of those as we go through. Okay, I cleaned that up a little bit using my little white marker. Just kind of scratch that out, and then I just wrote on top of that. So it says here that a company, let me get my pen back, a company is saying that their tires are going to last 39,000 miles. What percent of the tires are likely to wear out before 39,000 and get the refund? Well, that would be from these guys back. And so that would be, we've already added this up, that is the 2.5%. So 2.5% are to get a refund. And that would be all that they would need to do, and if they've collected appropriate data and they believe their data. So you do have to get good data in order to believe this, but if you test enough, then your data is very reliable with this standard normal. Next, we're going to look at scatter plots, and in this next scatter plot, we're going to examine the age versus height on children and see how that compares. So here we have age versus height. Notice we have, what this graph actually means is I have two students who are 6 and I have plotted their height here. I have 3 students who are 7 and I've plotted their height. I have 3 students who are 8 and plotted their height, and I'm supposed to decide if this has any sort of correlation, and I see that I believe the data is going up. That's a positive correlation, and it looks to be fairly linear. Not all of your data will make a line. Sometimes it'll make a parabola or a curve downward. So they're telling us that scatter plots are really nice if we're looking at businesses and plots. We're going to look at a bungee jumping experiment here in just a second and see how that data compares. So what the children did is they used weights and some rubber bands to see how far the rubber band would stretch and to see if there was a correlation there. Looks to me like there's definitely a correlation. It could be a little parabolic. It's got a little bit of a curve there. I'd have to collect a little more data to see if putting more weights really makes it rise a bunch, but it's probably going to be linear. And that's what they're deciding here. They think it is fairly linear, and I see this straight line look to my data. We call this a positive relationship because it has a positive slopes going uphill from left to right, and we think a straight line would be a pretty good fit. The correlation coefficient here, if it is close to a 1, is a really good fit. This means it's a positive correlation and it's a really good fit. If it is negative, it just means it's going downhill, and the closer it is to 1, the better the fit. That would mean this would look like this if we had data that was -1. If our correlation coefficient is 0, that means there is no relationship at all. Next, inferential statistics. Now if you take a statistics course, inferential statistics is what we're really looking for because we need to collect data from a sample. Now I can't collect all of the data from all of the tires like I had before. So I just take a sample, a random sample, and how you get that random sample is going to be very important. It is the thing that that has people saying that statistics lies, because if you take a sample from a particular group that you know will substantiate your claim, then that's not doing true statistics. That's kind of fudging the data. So we don't want to do that, although drug companies tend to want to do that so that you will buy their products. So you do have to be careful about where the sample is drawn from. Such as if we're talking about favorite sports teams of 4th graders. Well, it depends on where you ask those 4th graders. If you talk about favorite sports of 4th graders in the North, they may favor hockey over some fair weather sports such as water skiing. So it just depends, and you would have to be sure and collect a sample of data that was representative. Once again, talking about pulling your data from a good sample of something that represents what it is that you're trying to show. The last thing we're going to talk about would be weighted averages. Now, something that's very near and dear to you, I'm sure, would be the weighted average of your grades. Now, I'm not really crazy about this example, but we will do this one. The reason I don't like this example is because there's nothing to weight here. They're all worth 3 credits. But if you were to do it, you would say a grade of B is worth 3. So it's 3 times 3 plus 4 times 3 plus 2 times 3 plus 4 times 3 out of a total of, and that would be 12 credits. And this answer is, if I compute this, would be 3.25. So what I'm going to do, because this example really doesn't do it justice, let's go to this one, and I am going to change and make this computer science class, let's make it a 5 credit class and see what this does to my GPA. So this will be 3 times my 3 credit class plus 4 times this 3 credit plus 2 times a 5 credit class plus 4 times a 3 credit. My total number of credits now is not 12, but it is what, 14? Yes, so I'll compute this. So changing that C to a 5 credit class, my grades didn't change at all, but changing the weighting of those grades really changed this. Now it's a 3.0 instead of a 3.25, I think was the other one. Lastly, we're going to look at, let's see, we've got some grades here and we need to have a 2.5. So let's figure out how we're going to look at this. Now, this is worth 50 times 2.35. Let me get that number. Okay, so that's what I got. This is what we have. This is what we need to end up with. We've got to have a 2.5 in order to get into whatever program she wants to be in. So that's going to be 66 times, 2.5, and I have it calculated somewhere. It's 165. Reading it off my calculator. So this is what we need. This is what we have. So let me do 165 minus 117.5. So I need a total of 47.5 points. I'm going to take 16 credits. So what does my GPA need to be? I'll say 47.5 divided by 16. I'm going to need to have a 2.96875. So I best make all B's. And if I make all B's, I'll be good to go. I'll be able to bring my grade point average up. Alright, well that's all I have for this particular section. I hope you enjoyed it, and if you have any questions or if you need an extension, be sure and let me know.